Hello! In today's video, I'm going to talk about camshafts. Well, camshafts and RPM. We have all seen over the years camshafts tests, and they basically say, you know, the bigger the camshaft, the higher the RPM. And that kind of says the camshaft is controlling the RPM. Now, in some of the other videos, I have pointed out that's not really true. And I have said that the CFM demand formula is actually going to show you where the motor stops in RPM, because it's really about airflow. And so, what is the camshaft doing? What are these tests showing that we're not looking at? And that's what I want to talk about today. Now, remember, everything is pretty much controlled by inertia ramp. That is the main piece. And so we have to look at that in that light. We have to look at how the cam is affecting the motor and what we're seeing. Because if we just say a camshaft is based on a particular RPM, and some guys will tell you that, it's about the time, it's about the length of time, that as the cycles go up, the length of time shortens and you have to hold it open later. But we don't really see that always. And so what are we really seeing? Because if you take like a 235 cam and you put it in a 327 Chevy, it's a little bit rowdy. If you put that exact same cam in a 500 cubic inch Cadillac, you almost can't even tell it's there. The idle is a little bit lower vacuum, but it doesn't massively impact the motor. And the RPM band that the 500 runs at is substantially lower than what the 327 will run at. So if the camshaft timing is controlling the RPM band, then why is there a discrepancy between those two? It can't be. And so I started looking at some of this stuff, mostly in the 90s, but I'd see these articles. I kind of had the same idea. I started working in a speed shop. I'm having to recommend cams to people, and I'm having to adjust a little bit according to how big the motor is. And I started thinking that was a little odd. But let's look at the mechanism of what we are seeing. Why do we see certain things? So in one of those early tests, and I just drew something here. This isn't from any given test. There's plenty you can go look at if you want. But I drew basically a 210, a 235, and a 254. We're not even talking about what engine it's in, because we're just talking in general. And so what we see on a lot of these tests are, as you go up in camshaft, RPM starts to creep up. And that's where we get the idea that the camshaft controls RPM. And on some of these tests, you'll find when you go to the bigger cam, it doesn't really change a whole lot. You gain a little bit, but the RPM doesn't really shift up. And the guy writing the article might say, well, that really shows you that the middle of the road cam is really much more ideal for what we have here. That's not completely true. What's really happening? Because we know CFM, flow, is what controls RPM. So why do we see an increase with cam? Well, we see an increase because as cams go up in size, they go up in lift. The general lobe design is way easier to do if you keep increasing lift with duration. It's just there are acceleration, deacceleration curves. I'm not getting into any of that. If you want to learn more, you're probably better off going to Powell Cams, Daniel Powell, and watch some of his videos. He is going to be much better at explaining the cam lobe design. What we are talking about here is just generally what we see. And in these tests, they don't tend to use lift limit lobes, which is probably a good thing, because lift limit lobes a lot of times make a disaster out of the valve train. because the curves on acceleration are not right. And so we are going up in lift. If the head has more flow, that means because we're going up in lift, we're going up in flow, so we're going up in RPM. And that's really where it comes from. If you limit the lift, then you limit the shift towards RPM. And that's because you are basically limiting the flow. Now, you don't really want to limit flow if you can avoid it, because air is horsepower. But that is the trend you see. And so what happens with the rest of this? Because guys will tell you it's really about the time. It's really about, as you go up in RPM, you need more time to fill that cylinder because the cycle time gets shorter and shorter. Yet we don't always see that. That isn't completely true. And so what else are we seeing when we do this? We understand flow is going to change our RPM. And the inertia ram is changing the fill because we are holding that valve open later and later. But what happens when we hold that later and later? Well, if you take the same exact motor and you just keep putting cams in it, bigger and bigger and bigger, you keep moving this further and further and further down, then your airspeed demand, how much airspeed you need to overcome pulse back, goes up because you need to fill the cylinder. And that's what you start seeing here, is down at low RPM, you start losing power. Well, that's because you're getting pulse back. And you can see this. I have a link in one of the playlists in this channel to Kazi's clear intake with the intake running, with the motor running. And he puts his finger in, and it's crazy. What you're seeing there is really pulse back. The motor is a big motor. It's a big cross section. It doesn't have that much airspeed. It's at lower RPM. It's not at its peak. And it's showing you the pulse back coming back up the intake. And that's what we're talking about when we hold this open. Everything has a consequence. And as we move this down, we will lose power down here if we don't have airspeed to carry it. And so that's why you can't, a lot of guys will ask me, well, if this is power, if this is the percentage of VE, why don't we just come up here to 1.3, run 1.3? You know, the motor will make all sorts of power. Except for it doesn't. Because unless you have the airspeed to carry it, it will not fill the cylinder. And so when you just take a regular motor with a given CFM and you go bigger and bigger in cam, well, the airspeed required goes up. And that requires more RPM in order to gain that airspeed. And so you wind up with a motor that works better up here, but not down here. So I'm sure at this point you're saying, well, then why are you talking about RPM? Obviously, the later the closing, the more the lift, the higher the RPM. And like I said, if you take a test motor and you do one of these, you will see exactly that. And so you're like, they were right. They were right 20 years ago. They were right 30 years ago. But the piece you're not thinking about is airspeed. If you can fix the airspeed for the bigger cam, then you can make power down here. And that's really what you're trying to do. Now, we have struggled with how you fix airspeed because one of the easiest ways, one of the ways OE tended to do it, certainly back in the 50s and 60s, is they reduced the cross-sectional area, which reduced the flow and increased the airspeed to get better fill down here. I mean, that's how we even learned that you could open the valve longer is in way early motors. You go back into the 1900s, you look at some of the ports and they were just massive. It was basically just open it up and let the atmosphere in. Well, there was no airspeed at all. And that's why they couldn't go very far with the opening point or the closing point of the intake valve. As we learned that you need more airspeed, we learned you can pick this up more and more. Now there is an airspeed limit as to where you're going to go. And that's really what this is talking about. You are looking at the CFM of flow from a head. And you're looking at the RPM of the engine. I used inertial ram to make this at 100%. Well, the inertial ram formula is based on 28-inch flow. It was a test motor. It was meant for guys using the flow bench. It was meant to explain how some of this goes. And so it was probably a single cylinder test motor with a variable length straight intake. There was probably no taper, no bends, no nothing, because we're talking a single cylinder test motor. And they probably even had some way to vary the closing point and find the sweet spot on their test stand at a certain power to come up with this math. And this math is designed on a test motor. And it works because every engine runs the same way. If you have an engine that's a single cylinder Briggs & Stratton or some super exotic 16-cylinder aircraft motor, they all work on the same basic principle. And all of the math should work on every engine. If you have to keep changing a constant, this constant only works on a small block Chevy at 350 CID. If you go up to 400 or 428, then you need to use this constant. If you use a Mopar, you got to use this constant. That's not a formula. That's seeing a statistical trend in the type of motor you've been testing. And that's fine. That'll get you pretty close. But that doesn't really explain how the engine works. The math needs to work for everything because they all work the same way. And that's true of camshafts. They all work the same way. But if you start looking at it from the standpoint of airspeed, then you can see why you can get away with a bigger engine, a bigger camshaft. On the Cadillac 500, I'm fond of saying it swallows a lot of cam. Well, the reason it does that is it is a restricted port for the CID. And so the port volume, the amount of air you're moving per CID, per cubic inch, is not very high. And so you wind up with high airspeed. On a stock Cadillac, like I've been talking about doing that cam test, you come in, going to be down here like 300 hours, you come in and the torque curve is dead flat and then it falls off because you have airspeed right away. That's why you also have lots of vacuum on that motor. And those things are connected. Those are some of the things you can see. The reason a bigger and bigger cam makes less vacuum at idle is because you've required more airspeed, you're getting more pulse back, and you are lowering the amount of air that's getting moved, so the vacuum drops. And that's why your fill down here is terrible on a small block with a big cam. It's great up here, but it's terrible down here. But then you put the same cam in a big motor, especially a big restricted motor, and suddenly you're okay up here. And that's because it's really about airspeed. Now, if you're trying to make lots of power, one of the things you got to think about, especially if you're still trying to keep it flexible, If you don't pay good attention to airspeed, this power curve gets narrower and narrower. And guys have talked about that. If you've been in this and read magazines, watched things online, they'll talk about, well, the motor's getting a little peaky. Well, that's because they're really not doing that well on airspeed. So it's only really working well at the top of the RPM band. And they basically killed off the bottom. If they then worked on trying to increase the airspeed, then you can increase the width and the power that you're making. And so when you are building a motor, like I do mostly, street strip, it becomes more important to pay attention to what's going on with airspeed. You really need the intake to be well matched to the motor. And if we look at that, like I have talked about in one of the previous videos, say the intake is a little big, has a little too much taper, or you chose a single plane instead of a dual plane and you're really trying to work down here, what happens? And we talked about that a little bit. If the intake's tuned just a little bit higher in RPM than where you're going to be working with your airflow at your given lift, then you can get a little carryover. The airflow at its RPM is going to peak out horsepower. But then, because you have a little room in airspeed, you can plateau it and it will carry it just a little bit. And that helps you make it a little more flexible up here. And that's actually why you'll find guys, well, I just added a little taper, it was pretty good, and the taper really made it better up here. Well, they're just tweaking the length a little bit up and hitting the sweet spot. Now, if we go smaller in cross-section to drive up this airspeed, then we will move the RPM bit down, but we will also restrict airflow. If we restrict airflow, then we are going to lower the RPM and the power produced. Because remember, the power produced is based on inertia ram and the closing point. This is basically VE, and that's going to say how many CFM you are actually going to use at the given RPM. So what's the solution? Well, the other direction, it'd be to go to a long ramp. You go to a really long induction system, and what happens? Well, if you go low, what happens is the airspeed maxes out. You can actually hit, airspeed won't just keep adding and adding and adding. That's part of the reason I keep saying I think that the maximum airspeed is actually Mach 1 or just under. I don't have an easy way to physically measure what the airspeed is inside a runner. I have no way to put a sensor in there and tell me what it is. It's going to take somebody with more science and more data collection ability than I have in anything I do. So I just have to kind of look at what's going on. I look at a torque curve to decide where I'm making torque, because that's about VE. But what happens when you run a really long runner? Because it's like, okay, well, all the modern stuff runs a long runner, and if a long runner makes it work, why don't we just run something really long, like that crazy Acme intake I showed that's 22 inches long, 16 on the intake and the rest in the head. What happens if you run that? Well, Corny, when he's run those before, I've said, says that suffers from fuel shear. What I think it actually suffers from is an airspeed problem. Because if your airspeed maxes out, if you're coming up and you max out the airspeed, you're done. You are just going to, the power will come up, and we'll use the big camera. The power will come up, and then it does that. Airspeed's max. It can't go any higher. It can't get up. It may even nose down. I carried this out probably too far. It'll probably even nose down early because it's maxed out. And that's what happens if the runner's too long. That's why I keep telling people to pay attention to the inertia ram length as to what you need. Taper will shorten the runner, which if packaging is a problem, that can help you. But making the runner extra long doesn't help you either because it can kill the power. You wind up at whatever RPM that you hit peak airspeed, that becomes your CFM limit. If you reverse this formula, what you find out is if the runner's long, it'll peak early, and that RPM with that given displacement will come out to a CFM that's for the horsepower it just peaked at, because it's done. Airspeed ended what was going to happen. And you can see this probably most profoundly on a really long runner. And I thought about for a while, what is a good example of this? And then I remembered the old 413 long ramp. Well, Nick's Garage, one of the YouTube video guys, did a 413 years ago. I've always wanted to play with one, but they are so rare, I have never even seen one assembled and running. And so he did one on the 413, but it was a shorter ramp because Chrysler had two different lengths. And then later on, I don't know, 6-8 months ago, he did a 440 with the long ramp. So we got a big motor and a long ramp. And the nice thing is, he tested it with a single plane intake and a single carburetor, and then put on the long ramp. And you can actually see what happens if the runner length gets too long. It's a very good example because it made almost, not quite, made like 486 horsepower, I think it was, with the single carburetor, single plane intake. Then he puts the long ram on it, and the horsepower drops to just over 400, 403, and the RPM drops at where it's making power. And of course he talks about the fact, well, it's tuned for lower RPM, and talks about torque and all that. And that is certainly true. But it shows you that you have limits on airspeed. You can't go higher and higher and higher. This is why I kind of laugh when I see porters, well, you know, I'm going to run this one at 360 feet per second on my bench. That'll make good power in the engine, and that's my target. Well, you don't control that. The engine does. The engine does, excuse me, with the intake and the runner length. The cross-sectional, how much air you're moving, and the given length. Sorry about that. So you need to pay attention to what's going on with all the components. You want to try and run, which if you look at the trend, you want to try and run a bigger cam if you can get away with it. Because that will increase your volumetric efficiency. It will increase the horsepower you make. But as you do that, you have to try and compensate for what's going on. You either have to limit the airflow, which depending on the engine, it may be that way anyway. And you can bring the power band back down. Or you can not push this as much. Because that's the other thing that I get, even from some of the guys in the shop, is, well, why don't you just go up to a bigger cam? I want that bigger Z. I want that power. We need to make that big power. Well, it'll make that big power. I can make that big power up here. But what's it going to cost me down here? If I need the motor to be flexible, then I do have to watch how much I put into it in camshaft. But I'm always trying to err on the bigger side and then deal with it on the intake. And that's why I've said before, on occasion I've had to swap to a different intake and try and correct what's going on. But if I have killed it so much down here, I can lower what the intake does, try and drive up the airspeed, either a longer runner or a dual plane instead of a single plane. And that's, as you understand this, that's another dyno test you can now understand what's happening. When they test a single plane and a dual plane, you know, they take an Edelbrock RPM dual plane and then they test it against maybe even a Victor Jr., which is a small cross-sectional single plane, or they might go up to a Victor, which is bigger. You will see a big difference. And they will say certain things about what they're seeing. And one of it is, well, you know, yeah, we lost a little bit of peak power, but it does way better down here. Well, that's because the dual plane, by design, has more airspeed. But it also will limit how much airflow you have, which can cost you up here. And so a single plane is the same way. If you increase the cross-sectional area and you shorten the runner, you will drive down the airspeed. So then you need RPM to pick it up with whatever the given cam is. Now, a lot of guys will say, well, just run a smaller cam. Well, you run a smaller cam, you're probably going to be at less lift. You may have trouble hitting your horsepower goal. And so this whole thing is a juggling act. But the camshaft is kind of telling you how much you got to look at airspeed. Now, sometimes it can be less fussy. I mean, like the Cadillac 500 is a restricted motor. It kind of has airspeed no matter what. So my camshaft test, I'm talking about putting a big cam in it and see what happens. Now, I limited the lift, partly because stock valve train just can't take it, but also because I wasn't going to gain anything from lift. The heads just don't flow. The intake, which we have to run. Now remember, this particular motor I'm looking at has to have the stock intake, and then you might as well just run stock heads, because the stock intake is a problem. It can't flow nothing. Its top airflow is about 180 CFM per runner. It's nothing. 500 cubic inches, 180 CFM. That's why I think I have airspeed down here, because the torque on the stock comes in right away. So I'm hoping I have enough to carry it with the bigger cam, and I will still be down here in my power band, because I understand that the camshaft doesn't really control the RPM. It controls what's going on in the motor. It controls how much you need airspeed, and then of course the intake will decide where you're going to probably have that airspeed, how much it's going to generate. If we do really well putting in a big cam, I might be able to swap in a different intake and see at one point it just kills me down here to try and gauge where my airspeed is. Because like I said, I don't have an airspeed sensor that says, hey, down here I'm only at 320 feet per second. You know, but when I get up here, I'm at 780. I don't have a meter for that. So I have to try and look at what's going on and decide what's happening. And that's going to be the same thing if you're building a motor. Some of this we just have to test, because I just don't have an easy way to decide if it's going to be okay. I can make some really good guesses, so I'm not putting 23 different camshafts in it to find out what happens. But I need to make them good enough that the end result works out to what I want. The better you understand this, the better that comes out. If you make a mistake, if your particular motor is dead down here, you went with that 254 cam, and it did really good horsepower-wise, made lots. But you go to drive it, and it's terrible. And you're going to have to put in big gears. Well, you don't want to do that. The easiest fix is to try and drive up the airspeed. It may cost you peak, because as you drive up airspeed, it will cost you airflow. So crest suction, length, either way, it has limits. That's what's happening with that long runner. Maybe I should have explained that better. As you get longer and longer in runner, technically the airspeed goes up, but it has a max. And because you hit that max, basically you quit moving as much air. That's why it peaks at a lower RPM. And that's why guys will tell you, well, you need 7% taper or whatever. And that'll work on certain race applications, but it's not universal because it really depends on the rest of the combination. And I wish I had a formula for how much runner length taper takes out, because I have seen lots of motors that mathematically don't work out. They put a really big cam in, 125, 113. I mean, we're trying to get 30% over volumetric efficiency, but they don't have the airspeed to carry it. And they may have figured out runner length pretty accurately. They may have used Pipe Max, which is a popular program, to figure out runner length, but then they didn't realize by adding taper, they're shortening the runner length. So if they're going to add the taper, they're going to have to lengthen the runner length to get the airspeed to carry the closing point. They're basically, the motor will stall right at 100% VE if you don't have enough airspeed to carry it up here. That's why in most of the stuff, I recommend you stay in lower cams below like 256. Is because you need to stay in somewhere that you can function without having to have everything perfect. You start getting up here, and you better have the runner length exactly on, you better have everything working right, the cross section of the runner right. You really need it right to work up here and make extra power. Otherwise, you're just going to make power like that, and you might as well just put in a smaller cam. So that's camshafts and RPM. I know I kind of went off on some tangents, but the bottom line is the camshaft only slightly controls the RPM. It changes parameters that will change RPM. It will change your required airspeed that you need to make it behave well. It will change the CFM with lift. But that's all the camshaft is really doing. It's not really about time. And that may happen way up in RPM, but all the rest of this happens first. And so we don't see it. So that's camshaft versus RPM. I'm hoping this one's not too confusing. I've tried to lay it out. If there's a problem, let me know in the comments. Like I said, you ought to see at least the pulse spec video. It's in a playlist on this YouTube channel. It's Cassie's video, and it's a clear intake, and it's fascinating to watch because you really see what happens with really big cams, because that's going to be a really big motor, a really big cam, and a really big pulse spec. So I wish you well on your projects, and leave a comment if I've confused you completely, and I will try and do better. I know integrating all this is complicated, and I've said various things in various videos, and some people are getting confused. So let me know if this is any better. I'll try and lay it out. Like I said, if you want to see what happens with too much airspeed, Nick's Garage on a 440 long ramp. If you punch that into Google, it should get you there. And That's fascinating to watch just in the change in RPM, because that shows exactly what I'm talking about. Other than that, there's plenty of other videos out there with camshafts tests, and if you start understanding this, you should start understanding what you see when they do it, probably better than they do. So, wish you luck, and I'll talk to you later. Bye.